Dear students, welcome to this week's lectures, and we have reached chapter 5, in which we will talk about so-called risk-neutral option pricing. But before we do that, we define some theory, and in detail in section 5.2.1, we will talk about the Radon-Nikodym process and two corresponding lemmas that appear to be very handy and very important. So let's first remember what we have done before with the process, with the random variable z in order to do a change of measure. And the setting was as follows. Let, of course, omega fp be a probability space, and let ft, t greater or equal to 0, be a filtration, the usual setting. And then z is a random variable on omega, and it satisfies the following. The probability of z greater than 0 is 1 almost surely. And secondly, the expected value of z being the integral over our event space omega z dp is equal to 1. Under these two conditions, we had a new probability measure defined, a new probability measure on omega f, and it was defined as follows. And we called it p tilde, and p tilde of a was by definition the integral over our event space omega of the indicator function of a dp tilde, and that was defined as the integral over a of z dp. Remember, the indicator function gives us the change of integration range, z dp, where p is the standard measure here, and that is equal to the integral over omega, event space omega again, of the indicator function of a times z dp, and that we know is the expectation of the indicator function of a times z. This we have seen before, and we will make use of this change of measure in this section. Now it's easy to show that this is actually a measure. You show that the empty set has, of course, 0 p tilde measure. If you integrate the empty set, then the indicator of the empty set is equal to 0, and you end up here with the expectation of 0, which is equal to 0. And it is sigma additive. So if you have a disjoint sequence of sets, and you look at p tilde of a, so p tilde of the disjoint union of sets, and disjoint union is denoted by this union symbol with a dot inside, of sets aj. That is the expected value of the indicator value, the indicator function of the disjoint union of sets aj times z. And because it can be only in one such j, this is the expected value of the sum of j, of the indicator function of aj times z. And we can use the monotone convergence theorem. Remember that anytime your random variable inside the expectations are non-negative, you can always bring the sum outside the expectation sign. If they can be negative, you have to make sure that the absolute value is convergent, but that's a different story. But in this case, we can take the sum outside the expectation sign. So this is in fact equal to the sum over j of the expected value of the indicator function of aj times z. And this is in fact the sum over j of p tilde aj. And this shows that the measure p tilde is indeed sigma additive. Now, using a standard argument, one can show that for any random variable y on omega, one has the following: the expected value of y under the p tilde measure, that is defined as the integral over event space omega of y d p tilde, that is equal to the integral of y times z dp, and that is the expected value of y times z. So connecting left and right hand side, we see that the expectation of y under the p tilde measure is in fact the expectation under p of y times z. And we wrote using a standard argument, one can show that. Remember the standard argument. That was first, we look at indicator functions. Well, if we look at indicator functions, then we have the definition, right? The definition here. So that is true by the definition. Then subsequently, we look at simple functions, and these are finite linear combinations of indicator functions. And that is followed by positive function, where we take an increasing sequence of simple functions plus using the monotone convergence theorem, taking n to infinity. And finally, for a general random variable, we split into two functions with positive and negative parts and finalize it this way. Now, given what we have just seen, we can simply write dp tilde is equal to zdp. And that is, again, a matter of notation, differential notation. And we would like to make a remark here. Because the probability of z greater to 0 is equal to 1 almost surely, one has that p and p tilde are in fact so-called equivalent measures. And that means that the probability of A, when the probability of A is equal to 0, that implies that the probability of A under measure P tilde is equal to 0 and vice versa. And we can see that easily from the definition. The definition, when the probability of A under the P tilde measure is equal to 0, if we go to the right-hand side with Z, the probability of z greater 0 being 1 almost surely, that implies that the indicator function of a should be equal to 0 here. And with the indicator function of a equal to 0, we will also have that the probability of a under measure p is equal to 0. So from the definition, it follows that, that these are equivalent measures. And equivalently, we can write the probability of A is equal to the integral over A of 1 over z dp tilde, or again in differential notation, dp is 1 over z dp tilde, and moreover, the expected value under measure p of y is the expected value under measure p tilde of y over z. And we denote that, that c as dp tilde dp, and we call that the Radon-Nikodym derivative of p tilde with respect to p. So z is dp tilde dp, the so-called Radon-Nikodym derivative. Now we are ready to define the Radon-Nikodym process. I've mentioned before that given a random variable, in general, you can use it to define a process which is a martingale. So we start with this z, which is non-negative, almost surely, and has expectation 1. Then the Radon-Nikodym process, which is denoted by zt, is defined as follows. It is defined zt as the conditional expectation of z given ft, where ft, t greater equal to 0, is some filtration. So we start with a filtration, and usually it will be the filtration of a Brownian motion, as we will see later on. And we will make a remark about it, and the remark is that this process is in fact a martingale with respect to the filtration ft. And that's easily seen with the help of iterated conditioning, whereas because for s less than t, fs is contained in ft, and hence the expected value of zt given the filtration up to time s, that is by iterated conditioning the expectation of this process, where we have substituted the definition, so the expected value of z given fs given given ft given fs, and that is the nothing but the expected value of z given fs, which is the definition of cs. So zt is a martingale. And we call zt, t greater equal to 0, the Radon-Nikodym process, which is associated to the Radon-Nikodym derivative z. What I'd like to do right now, as we have two measures that are related via the integral, we would like to know how to relate their expectations. If we know one expectation, how can we go to the other? And we will ask the same question for conditional expectations. And it is lemma 5.2.1 in the book, which helps us here. And remember this lemma, please, because it's very handy and we will use it all the time. Let's first recall the setting. In fact, the expectation of y under measure p tilde is, in fact, the expectation under measure p of y times z, where y is a random variable, so y is ft measurable. And we have a filtration, ft, t greater equal to 0. That is a filtration for which we have defined the Radon-Nikodym process zt. And again, y is a random variable, which is ft measurable, and ft is contained in f, in script f. Then the expected value of y under measure p tilde is in fact equal to the expected value of y times zt, where zt is the Radon-Nikodym process. So rather than computing the expectation of y times z under measure p, it is sufficient to compute the expectation of y times zt under measure p. So this is a lemma which allows us to calculate the expectation using less information, ft measurable functions here. These ft's are in the original sigma algebra f. I have a y which is ft measurable, and I have only information here which is known up to time t. Yeah? I don't need to know all the information which my original sigma algebra contains. I only need the information up to time t. And with this information, I can calculate the expectation of y under p tilde. So I know how to do this here, on the left-hand side. I know how to do this with yz. But again, to determine random variable z, you really need the whole information. But the Radon-Nikodym process gives you approximations of z up to time t. So I only know up to time t the information. How can I approximate z? And the best approximation of z is zt. It is the conditional expectation of z given ft. So the new contribution here is that this expectation will be equal to the expectation of y, and we have zt instead of z. And the proof is again a one-liner. So if we look at the right-hand side, the expected value of y times zt, there we can just substitute the definition of zt. So that is the expected value of y times the conditional expectation of z given ft. And y is ft measurable, so y can be taken under this expectation sign. So this is nothing but the expected value of y times z given ft. Iterated conditioning gives us, in fact, the expected value of y times z, and that is the expectation of y under measure p tilde. And here we have used the measurability, the ft measurability of y. So if you know that a random variable is ft measurable, and you have calculated its expectation under p tilde, and you want to transfer it to the expectation under p, you don't need to use z, you can use zt instead. We have another analogous lemma, which is lemma 5.2.2. And this is for conditional expectations. And please also remember this lemma as it is also an important and often used lemma. Let ft, t greater or equal to 0, be a given filtration, and suppose y is ft measurable. Then, in this case, we have for s less than t, that the expectation under measure p tilde of y given fs, so the conditional expectation under p tilde of y given fs, that is equal to 1 over cs times the conditional expectation under measure p of y times zt given fs, where zt is again the Radon-Nikodym process. So this looks a little bit differently with this 1 over z, but it's also an important one. So how do we prove this? Well, first of all, recall again that the expectation of y under measure p tilde is in fact the expectation under p of y times z. And remember that y is a random variable, so y is ft measurable. So to prove this result, it's sufficient to show that this right-hand side is the conditional expectation of y given fs under measure p tilde. So we start with the right-hand side and we go to the left-hand side in our derivation. Well, first of all, we need to verify the two defining conditions of these conditional expectations. Well, first of all, clearly the right-hand side is fs measurable. 1 over cs is fs measurable. And also this conditional expectation given fs is by definition fs measurable. So z inverse is fs measurable, and the same holds for its second term because it is the conditional expectation given the knowledge up to time t that is by definition fs measurable. So the product is also fs measurable. But now we need to really go from this side to this side, and we need to do the derivation. So what we need to show is that for a in fs, we want to show that the integral over a of 1 over zs times the conditional expectation of y zt given fs dp tilde is the left-hand side, the integral over a of y dp tilde, and that is in fact the expected value under measure p tilde of the indicator function of a times y. So let's get started, and let's first write this down a little differently. This integral over a of 1 over zs times the conditional expectation of y times zt given fs dp tilde, that is conditional expectation under measure p tilde of the indicator function of the event a times 1 over zs times the conditional expectation of y times zt given fs. Now, if you look at this, you see that this is in fact fs measurable. So we can take it under the second expectation sign, and we do that in the next step. So this is in fact the expected value under measure p tilde of the expected value under measure p of the indicator function of event a times 1 over zs times y times zt given fs. Now here we are in the familiar setting, and we can use lemma 5.2.1. Remember lemma 5.2.1? The expected value of y under measure p tilde is in fact the expected value of y times zt under measure p. So we are going to use that now. So the expected value under measure p tilde of this expression is in fact zs times this expression under measure p. So this is the expectation under measure P of CS times the conditional expectation under P of the indicator function of A times 1 over CS times Y times CT given Fs. Now this one is also Fs measurable, so we can take it under the expectation sign, and if we take it under the expectation sign, it cancels out with this one, right? So what remains is the expected value under P of the expectation under P of the indicator function of A times Y times CT given Fs. So the inner one is a conditional expectation and the outer one is a regular expectation. And this is in fact, we know that too, that is the expectation of this inner argument. So the expectation of the indicator function of A times Y times CT. Now again, using lemma 5.2.1 in this case, gives us that this is in fact the expectation of the indicator function of Y, of A times Y under measure P tilde. And this is by definition the integral over A of Y dP tilde. And that is what we wanted to show. So we have just shown that the right-hand side is in fact equal to the left-hand side, that 1 over Zs, the conditional expectation under measure P of YZT given Fs is in fact the conditional expectation under measure P tilde of Y given Fs, and that is what we wanted to show in lemma 5.2.2. And that concludes the first part of today's lecture. Thank you for your attention.